We're now going to start talking about field extensions. A great deal of field theory has to do with the relationships between fields where one is contained in another or essentially contained in another. Let's start with definition 156. Let's let F and E be fields. We say that E is an extension field of F if there exists an injective ring homomorphism phi from F to E, which is called a field extension. So we'll refer to the field E as an extension field and the homomorphism phi as a field extension. In particular, the most common situation where we encounter this is that this holds if F is contained in E and the operations on F and E agree. In which case we can just take the field extension to just be the identity, which takes every element to itself, because F's a subset of E. That's a function from F to E, and it's a ring homomorphism because the operations on F and E agree. Now, given two field extensions, phi from F to E1, phi1 from F to E1, and phi2 from F to E2, we want to describe a class of homomorphisms of extension fields. A function psi going from E1 to E2 is a homomorphism of F extension fields if, first of all, well, psi has to be a ring homomorphism because E1 and E2 are both rings, they're both fields. And we have to have that psi of phi1 of x is equal to phi2 of x for all x in F. And then if psi is bijective, it's an isomorphism of F extension fields. All right, so we can illustrate what's going on down here with a homomorphism of F extension fields using a figure known as a commutative diagram. So the situation is that we've got a function F and we've got two injective ring homomorphisms to E1 and to E2, where E1 and E2 are the extension fields of F. And then psi here is a homomorphism of F extension fields if, when you go from an element of F to an element of E1 and then use psi to go from there to an element of E2, you get the same thing as if you applied just phi2 of x to x to begin with, and the condition on psi being a homomorphism, an F extension field homomorphism, is that these two values have to coincide. So this is often illustrated this way with a curved arrow inside the diagram, indicating that no matter which way you get from F to E2, whether you go along phi1 and then psi, or you go along phi2, you get to the same value. And so this is what it means to be a homomorphism of F extension fields. Now, most of the time when we talk about extension fields, we talk about them as subsets of one another. Now, common examples of field extensions that we are used to are the field Q sitting inside the field R, the field R sitting inside the field C, and so forth. Now, one of the most important properties of these field extensions, and indeed field extensions in general, is that polynomials over some of these fields don't have roots, but they do have roots in the extension field. So for instance, if we let f be x squared minus 2 inside the polynomial ring over Q, this has no roots, but if we take f to be x squared minus 2 inside of R adjoin x, this has roots. In fact, it has two roots, plus and minus the square root of 2. And similarly, you can look at, for instance, the polynomial x squared plus 1 inside the polynomial ring over the reals has no roots, but it does have roots over the complex numbers. As we saw back when we were talking about factorization, any homomorphism, any ring homomorphism from one field to another, such as a field extension, induces a homomorphism on the level of polynomial rings with those fields as coefficient rings. We're going to take advantage of that quite a lot. So recall that if phi from F to E is a field homomorphism, this induces a homomorphism phi bar from F adjoin X to E adjoin X, where we apply this to a apply phi bar to a polynomial a0 plus a1x plus etc. plus an x to the n by simply applying the function phi to each of the coefficients. We're going to be taking advantage of this construction a lot, and we're always going to use the overbar notation on a field homomorphism to mean this function on the level of polynomial rings induced by a field homomorphism, or in particular, a field extension, as we are typically going to do it. Now, one of the most important theorems in field theory is sometimes called the fundamental theorem of field theory. And it was proven by Kronecker. It tells us that if f is any field and little f is a polynomial in the polynomial ring with coefficients in f is a non-constant polynomial, there exists a field extension phi from F to E such that phi bar of F inside E adjoin X has a root. So you take any polynomial over any field, there is some field extension of that field such that the image of that polynomial in that extension has a root. In fact, we're going to be able to go much further. We're going to be able to apply this multiple times to get up there, but this is the first step, showing that we can always get a root of any polynomial we choose, no matter how irreducible it is that we're working with. In fact, irreducible polynomials are where we want to start. Before we prove this, we need another theorem, which is going to be very useful in its own right. So Theorem 158 says that if F is a field and little f inside f of x is irreducible, then the ring, which is the polynomial ring over F, the factoring when you mod out by the principal ideal generated by F, this is a field. So the quotient of a polynomial ring over a field by the ideal generated by any irreducible element is itself a field. Let's prove this. Now, remember that quotienting by an ideal gives you a field if and only if that ideal is maximal. So we're going to be proving that the ideal generated by an irreducible element in f adjoin x is maximal. So let's let I in the ideal generated by f of x be an ideal such that the ideal generated by f is contained in the ideal I and is not equal to I. Now, f adjoin x is a PID. Polynomial ring over any field is a principal ideal domain. So that means that I is a principal ideal generated by G for some G in the polynomial ring over F. Now, since F is contained in I, which is the ideal generated by G, we have that F is equal to G times H for some H in F adjoin X. Now, we have assumed that F is irreducible, which means that anytime we write it as a product of two things, one of those two things has to be a unit. So since F is irreducible, G or H is a unit. Now, if H is a unit, then that means that F is equal to G times a unit, which means that G is equal to F times some unit, the inverse of H. And in particular, then that means that G is contained in the ideal generated by F. So that means that I, which is the ideal generated by G, is contained in the ideal generated by F, which is a contradiction. Because this would imply that I is equal to the ideal generated by F, and our assumption was that they were not equal. So that means that G is a unit, and so I, which is an ideal containing a unit, has to be the whole ring. So in conclusion, the ideal generated by F is maximal. So by Theorem 104, F adjoin X mod F is a field. Now, the way that we're going to use this, one of the ways we're going to use this is in noting that this field here is very naturally a field extension of the field F. Under the map that will take an element of F and take it to the equivalence class of with representative, that constant polynomial inside this field. So this is going to be the extension field that we use to prove Theorem 157. Okay, so now let's do that. Let's do a proof of Theorem 157. So let's let F be a field. F in F adjoin X, a non-constant polynomial. Now, since F is a unique factorization domain, F has an irreducible factor G, which we'll write as A0 plus A1x plus etc., plus an x to the n. What we're really going to show is that G has a factor in an extension, it has a root rather, in an extension field of F. And then since G is a factor of F, that means F will have that same root in an extension field. So now we're going to let E equal F adjoin Y divided by G tilde, where G tilde, another way we could write this would be G of Y. This is just what we get when we replace all of the x's with y's in the expansion for G. Now y is a new indeterminate here, but when we take this field here, notice that G tilde is irreducible in F adjoin Y, and that's because G is irreducible in F adjoin X, and all we've done is we've replaced X's with Y's, just a relabeling. And so that means that E is a field by Theorem 157, which we just proved. Okay, so we're going to claim that this field, E, does what we want. It's a field where we can construct a field extension from F to E, where the image of little f under the induced homomorphism there has a root. So now let's let phi from F to E be given by phi of A is equal to A plus G. Remember that every element of E looks like some polynomial in Y plus the ideal generated by G tilde. And so we have B bar, which goes from F adjoin X to E adjoin X. Now this ring right here, E adjoin X, it's a little bit strange to think about. It's polynomials in the variable X where the coefficients of the powers of X are elements of E. So the coefficients of X in this ring look like polynomials in Y plus the ideal generated by G tilde. Okay, so now, since the degree of G tilde is greater than or equal to 1, G is irreducible, and so it must have a positive degree, we have that the kernel of phi is is only the zero element. It can't, anything in the ideal generated by G tilde has positive degree, and therefore the only thing that phi will send to zero will be the zero element. So that means that phi is injective, and thus phi from F to E is a field extension. All right, so we started with our polynomial. We constructed a field extension. It is now up to us to show that phi bar of F has a root in E. Okay, so let's go to a new page for this. We claim that y plus G tilde, which is an element of E, is a root of phi bar of F. Now, since phi bar is a ring homomorphism, we have that phi bar of G is a factor of phi bar of F, and so it suffices to show that y plus G tilde is a root of phi bar of G. So let's see what that looks like. Now phi bar of G is equal to A0 plus G tilde plus A1 plus G tilde x plus A2 plus ideal generated by G tilde, ideal generated by G tilde x squared, etc., plus an plus the ideal generated by G tilde x to the n, because each of these coefficients here are phi of A0, phi of A1, etc. Now, if we start combining, notice that this is an element of E adjoint X. So now let's see what happens when we take this polynomial, phi bar of G, and evaluate it at the element y plus G tilde. So phi bar of G is a polynomial. Let's evaluate it at y plus G tilde, which is an element of E. So this by definition will be A0 plus G tilde plus A1 plus G tilde times y plus G tilde. I won't do the middle ones, up to an plus G tilde times y plus G tilde to the n. Now, when we simplify all this down, because of the way that that things work in factor rings, first of all the powers of the y plus G tilde pieces can be pulled inside. So y plus G tilde to the n is the same as y to the n plus G tilde, and the same with y squared, y cubed, etc. inside. So now each of these products, A1 plus G tilde times y plus G tilde, for instance, by definition, are a1y plus g tilde plus etc. plus an times y to the n. This is just what multiplication looks like inside E. But now addition inside E is obtained by just adding up the representatives. So this is a0 plus a1y plus etc. plus an y to the n plus g tilde. But now notice that this representative here, a0 plus a1y plus plus an y to the n, is exactly g tilde. So this is exactly 0 plus g tilde. And that shows that y plus g tilde is a root of phi bar of g. Now, because phi bar of g is a factor of phi bar of f, that means that y plus g tilde is a root of phi bar of f. So we have finished the problem and shown that we can construct this extension field of f where the image of f under the field extension has a root. So using this theorem, we can construct fields that contain roots of literally any polynomial that we write down. Non-constant, of course. So, for example, let's construct an extension field of Q containing a root of x cubed minus 2, polynomial in Q adjoint x. Now this polynomial does not have any roots inside Q, but Theorem 157 tells us how to construct a field extension of Q in which this polynomial does have a root. Now, first of all, notice that x cubed minus 2 is itself irreducible. So we can let E be the field where we take Q adjoin Y, so polynomials in the indeterminate Y over Q, mod by y cubed minus 2. Now, it turns out that this is isomorphic as rings to the field Q with polynomial Q adjoin the cube root of 2, which can be written as a plus b times the cube root of 2 plus c times the cube root of 4, where a, b, and c come from Q. We're going to get much more into this as we continue on in this section. We're going to talk about how we construct fields and describe fields that have roots of polynomials in various ways. But the big point of this section is that we have this universal way of constructing extension fields that contain roots of irreducible polynomials. And it's going to turn out that we can leverage that to a significant degree.